Welcome back to my CCSP exam cram series, and in this second installment, we'll be covering every topic in the official exam syllabus for Domain 2 of the CCSP exam. As a cybersecurity strategist and a VCSO for a regional bank, I see a lot of real-world value in the skills tested in the CCSP exam. I think we can all agree that knowledge of cloud security is essential to be successful in today's job market. More importantly, last year I helped hundreds of thousands achieve cybersecurity certifications, like the Security Plus, the CISSP, and now the CCSP exam, all without expensive boot camps, and I can promise you this series will do the same. Now, in this series, you'll find one video for each domain of the CCSP exam. Today we're focused on Domain 2, and I'll provide a consolidated full course video when the series is complete. So Domain 2 is Cloud Data Security. And as always, to accompany this video series, I recommend the official CCSP exam study guide and practice test bundle to give you a great resource for targeted reading and self-testing. It comes with 1,000 practice questions, 2 practice exams, as well as some flashcards for review. You can find a link to the latest copy of the bundle and least expensive in the video description. And to further augment your review process, I'll provide a PDF copy of the presentation. You'll find a link available in the video description. And in that video description, you'll also see a clickable table of contents so you can skip forward and back through the video as your study requires. So let's get into Domain 2, Cloud Data Security. And I will cover every topic mentioned in the official exam syllabus. I will also provide examples and concepts when possible, and in this particular installment, I'll actually provide a little show and tell in a couple of cases in a live cloud environment, just to give you that additional bit of context to ensure that these concepts really sink in. This is a multiple choice exam, but a little real-world exposure always helps. Let's take a quick look at the exam essentials, those areas the official study guide says will factor prominently on exam day. We have risk and controls in each phase of the cloud data lifecycle, which risks appear in each phase, and which controls should be used to address. Various cloud data storage architectures. We touched on these in the building blocks in Part 1. We'll expand on that coverage here in Domain 2. How and why encryption is implemented in the cloud, the role of cryptography, encryption, key and certificate management, HSM, practices of obscuring data, masking, anonymization, tokenization, and a few others. Elements of data logging, storage, and analysis, and the importance in the data lifecycle, as well as the importance of egress monitoring. So this will include data loss prevention, identification through tagging, pattern matching, and labeling. What you really see here is the role of all of these in the cloud secure data lifecycle. So we need to be familiar with these technologies, but also where and why we apply them throughout the secure data lifecycle. Data flows and their use in a cloud environment. And we'll take a look at an actual data flow diagram I put together for you so you can see the concept in action. The purpose and method of data categorization and classification. So how to assign data categories and classifications, as well as data mapping and labeling. Again, all in the context of the secure data lifecycle. Roles, rights, and responsibilities of data ownership. So roles like data subject, owner, controller, processor, and custodians. We'll touch on the most important roles for this exam. Data discovery methods, the difference between structured, unstructured, and semi-structured. We see that semi-structured category pop in with the 2022 update of this exam. Objectives and tools for information rights management, and finally policies for data retention, deletion, and archiving. So retention and disposal formats, which we touched on in Domain 1, and how these affect regulations and our policy lifecycle. So in Section 2.1, which is described cloud data concepts, we'll get right to it, starting with a look at the cloud data lifecycle phases, where we need to apply these technologies to our data throughout its lifecycle. We'll touch on data dispersion as well as data flows, and we'll have a look at the data flow diagram I mentioned a moment ago. Now, the Cloud Secure Data Lifecycle, this is the model put forward by the Cloud Security Alliance, and it starts in the create phase. Data can be created by users. A user creates a file, for example. Data can also be created by a system. A system logs user access, for example. Now, in the store phase, to ensure data is handled properly, it's important to ensure data is classified as soon as possible. Only through classification can we apply appropriate security controls. And ideally, data is encrypted at rest, and in the cloud, that is doubly important. In the use phase, data should be protected by adequate security controls based on its classification. And sharing refers to any time data is in use or in transit over a network. Next, we have the archive phase. Archival is sometimes needed to comply with laws or regulations that require retention of data. And finally, the destroy phase. When data is no longer needed, it should be destroyed in such a way that it is not readable nor is it recoverable. Crypto shredding happens in this phase. We talked about crypto shredding as a more secure method of data destruction, and if you see a question on the exam around data destruction, odds are crypto shredding is going to be the answer. You'll want to know the cloud secure data lifecycle well for the exam, and we'll touch on various phases of the secure data lifecycle throughout this domain. Data dispersion. This is a core principle of business continuity that says it's important that data is always stored in more than one location. In other words, data is dispersed across multiple locations. And this is actually easier in the cloud because the CSP owns the underlying complexity that delivers site-level resiliency. And cloud storage for IaaS includes several different levels of storage redundancy, including local, where we see replicas within a single data center, zone, where we see replicas to multiple data centers within a region, and global, where we see region-level resiliency, where replicas are backed up to a backup region. We talked about those local, zone, and global concepts back in Domain 1 in Section 1.2. So data flows. Let's take a look at a data flow diagram, which is useful to gain visibility to ensure that adequate security controls are implemented throughout our cloud infrastructure. So for example, in our CSP environment, this may be Azure, AWS, Google Cloud Platform, we may implement a database subnet, which would typically be private, an app subnet, also often private. So by private, I mean not directly accessible from the internet. Then we have our perimeter subnet. This is internet facing. So we may have an API gateway, we may have a web app firewall for user requests coming to our website. But you see here we have micro-segmentation, so we've carved up our network so we can secure these individual workloads appropriately to restrict ingress and egress, only allow traffic from expected endpoints on expected ports. And then we'll map the flow of data through our infrastructure based on the types of requests. So for example, a system API request, and we see the data flow. We'll map our user request, a typical HTTP request coming through a web app firewall hitting a front-end website, which may also hit that back-end database. But you see we've called out authentication and authorization here. And we have our data flows and our security controls we can call out at each layer as appropriate. So we talked about network security groups as an example back in Domain 1. So just an example, but that is basically the data flow diagram concept. You're going to map out your infrastructure, your application, your data flows, and your security controls. And you'll want to be familiar with the benefits of the data flow diagram for the exam. So our benefits include decreased development time and faster deployment of new system features, and with reduced security risk. Visibility into data movement, which is going to be critical for regulatory compliance where data security is often mandated in law. So we need to understand how our data is flowing so we can add appropriate security controls at every layer. Encrypting at rest, encrypting in transit, encrypting in use. So some compliance frameworks actually require data flow diagrams to capture specific information like geographic location of data flows or ownership of systems where data is flowing. Bottom line, creating that data flow diagram can be both a risk assessment activity and a crucial compliance activity. So moving on to 2.2, which is design and implement cloud data storage architectures. So here we'll touch on storage types as well as threats to storage types. Now, for the exam, you'll want to be familiar with the types of storage and the security concerns associated with storage for all your cloud computing categories. So we're talking about infrastructure as a service, platform as a service, and software as a service. Now, if you watched Domain 1, you may recall we covered the storage types in the building block technology section of Domain 1. If you've not watched the Domain 1 video, definitely worth going back and having a look. But I'll go ahead and touch on these again briefly here. So starting with the IaaS category, we have raw storage. That would be physical media. And in the private cloud world, that's what we'd use to map a VM to a storage LUN on a storage area network. Volume storage attached to an IaaS instance. So there we're talking about a lettered volume in the form of a virtual disk. And then object storage, that's your S3 storage bucket or Azure storage, where you commonly see blob storage. In the PaaS category, we have structured data, that's your relational databases like SQL, MySQL, Postgres, and then unstructured or big data, sometimes called NoSQL. And in the SaaS category, we have information and storage management, that's your data entered via the web interface of a SaaS solution. Content or file storage, so that's your file-based content like you'd see with Box, Dropbox, OneDrive. Ephemeral storage, that's any temporary data storage for cache, buffer, session data, swap volume. And then finally, content delivery network. That's geo-distributed content for a better user experience, or UX for short. So we see CDNs used to place content closer to users around the world to deliver that content more quickly, be that web content, file content, video content, etc. These are just a few key examples, not an exhaustive list, but I wanted to make sure you're prepared for the exam. Let's shift gears and look at threats to storage types. So there are universal threats to data at rest, regardless of location, be that on premises or in the cloud. Naturally, we're going to be more focused on the cloud in the CCSP exam. But let's start with a look at universal threats from the perspective of the CIA triad. So unauthorized access threatens confidentiality. Improper modification of data threatens integrity. And loss of connectivity threatens availability of that data. Other threats include jurisdictional issues, denial of service, data corruption or destruction, theft or media loss, malware and ransomware, and improper disposal. Now, all of these can happen in the cloud. It's largely a question of who's responsible for prevention and recovery. So let's run through these one by one. So we'll start with unauthorized access. So a user accessing data storage without proper authorization presents an obvious security concern, right? The customer must implement proper access control. The CSP must provide adequate logical separation. If we go back to the shared responsibility model, we'll remember that a customer has responsibility for access control, at least to some degree, even in the SaaS model. Unauthorized provisioning. So this is primarily a cost and operational concern. So ease of use can lead to unofficial use, unapproved deployment, and unexpected cost. That unapproved deployment and unexpected cost comes from what we call shadow IT, a very common issue where folks lay down a credit card, they start using cloud services that aren't formally approved by the IT department. Then loss of connectivity, pretty straightforward. Loss of connectivity for any reason, whether that's network connectivity, access controls, authentication services, that takes away availability of our data. Jurisdictional issues. So data transfer between countries can run afoul of legal requirements, regulatory requirements, and privacy legislation bars data transfer to countries without adequate privacy protections. And the customer definitely bears some responsibility. By customer, I mean the consumer of cloud services. Certainly in the GDPR context, when I think about businesses in Germany, a customer using a cloud, which would be a business, is going to bear responsibility for making sure they meet the privacy requirements, the laws and legislation of the country of origin. And then denial of service. So in the event a network connection is severed between the user and the CSP, your CSPs are going to be better prepared to defend against distributed denial of service attacks and other disruptive attacks at scale. They have the infrastructure to support it. They have the services in place. Many of your large CSPs have built-in DDoS defenses that they don't even charge you for. Protections that you may not even be aware of as a customer of those CSPs. Then there's data corruption or destruction, so that's human error in data entry, malicious insiders, hardware and software failures, natural disasters that render data and storage media unusable. So some of these issues intentional, others maybe not. But all concerns we must protect against. That means implementing least privilege access, role-based access control, or RBAC we call that, and off-site data backups. Then we have theft or media loss. So in the cloud, CSPs retain responsibility for preventing the loss of physical media through appropriate physical security controls. Even in the infrastructure as a service model, where we have physical servers with hypervisors hosting our VMs, where the customer has the most responsibility of any cloud model, the CSP still owns the care and feeding of the physical server and the associated physical media. Malware and ransomware. So ransomware not only encrypts data stored on local drives, such as in an IaaS model, but it also seeks common cloud storage locations like SaaS apps. So think Box, Dropbox, or OneDrive. Ransomware that infects an endpoint, a client endpoint like a Windows workstation, will try to crawl into those SaaS folders and encrypt that data. Responsibility there is going to vary by cloud category, though. Improper disposal, so ensuring that hardware that has reached the end of its life is properly disposed of in such a way that data cannot be recovered. Now in that case, the CSP is definitely responsible for hardware disposal. I want to shift gears and talk ransomware for just a moment because this is such a significant threat to virtually every organization. So we have some common countermeasures to ransomware. So backing up your computer, storing those backups separately, so if the files on a computer are encrypted, we can restore those from an alternate location. File auto-versioning is very handy, so being able to revert to a previous version of a file. Now, some of your cloud-hosted email and file storage services ease that process. Microsoft OneDrive is one that comes to mind that offers access to 500 previous versions of a file. Although you can imagine that's handy, it's also going to be very labor-intensive if you're restoring files one at a time in that fashion, so that's where a backup stored offsite can come in very handy, and perhaps backing up all the files in your SaaS service. So, preventative techniques. Updating and patching computers, just shutting the door on known vulnerabilities. Using caution with web links and email attachments. Verifying email senders, and email is the most common way in the door for ransomware attacks through web attachments and email attachments that are carrying that malicious payload. We really just need to be careful what we open. Now, there are preventative software programs that give us protections at the email layer that will detonate email attachments, that will check web links to make sure they're not malicious before we are directed to that link. There are AI-driven cloud services that offer help with these. So you'll find endpoint-focused services, XDR, whether that's Microsoft 365 Defender or any of your third parties. You have email-based protections in services like Proofpoint or Microsoft Defender for Office 365 that give us those email protections with the detonation chamber to make sure that our web links and our attachments are safe. But user awareness training, that's the most important defense of all. If we can teach our users to exercise caution when looking at messages from external senders and being careful about the links that they click and the attachments they download, that's going to be the best way to prevent ransomware exposure. So let's talk regulatory compliance. So certain cloud service offerings may not meet all the organization's compliance requirements, which leads to two security concerns. And the customer bears responsibility in making sure that the services they are subscribed to meet the organization's compliance requirements. But our two main concerns here are the consequences of non-compliance. These can include fines or even suspension of business operations. The second is data protection. Now, requirements may include the use of specific encryption standards, handling, retention, the geographic location where the data is stored. Now, all the regulatory standards you need to be prepared for this exam are going to be covered in this exam cram series. I'll be touching on them throughout the 6 domains, but if I don't mention it, it wasn't called out in the exam syllabus. And that brings us to 2.3, Design and Apply Data Security Technologies and Strategies. In this section, we'll touch on encryption and key management, hashing, data obfuscation techniques, including masking and anonymization, tokenization, data loss prevention, a big topic in and of itself, as well as management of keys, secrets, and certificates. And certainly at least a couple of these topics are areas I find folks tend to be a bit less familiar. So we're going to touch on some fundamentals. I'll provide clear explanations, examples where I can, and we'll even jump over into a cloud service provider portal and look at a couple of services so you can see these concepts in a real world context. Now, this is a CSP agnostic exam. It doesn't focus on any one cloud service provider, but it always helps to see examples, and I'll provide those where I can give them to you. So let's start with symmetric versus asymmetric encryption. Symmetric encryption relies on the use of a single shared secret key. Now, it lacks support for scalability, easy key distribution, and non-repudiation. And by scalability, I mean scaling from one to many users, because key distribution is a real challenge with symmetric encryption on its own. Asymmetric encryption relies on public-private key pairs for communication between parties. It supports scalability, easy key distribution, and non-repudiation. Symmetric encryption tends to be faster, therefore it's used for bulk data encryption. Asymmetric encryption is scalable. It's easy to scale to many parties, so we often use asymmetric encryption to distribute keys for symmetric algorithms. The two can work together in that respect. Encryption is a difficult topic for many, so we're going to dig just a bit deeper here. So, symmetric encryption, to touch on this again, the sender encrypts the data using that single shared key. The recipient then decrypts that data using that same shared key. In asymmetric, we see the sender encrypting data using the public key of the recipient, and the recipient decrypts the message using their own private key. So let me put that into an example to make it a bit more clear. So we have Franco, who sends a message to Maria requesting her public key. Maria sends her public key to Franco. He then uses Maria's public key to encrypt the message and sends it to her. Maria uses her own private key to decrypt the message. Because that private key is unshared, and that is the only key that can decrypt the message that was encrypted with Maria's public key, we know that only Maria will be able to decrypt that message, assuming she has kept her private key private. So recapping there on asymmetric keys, public keys are shared among communicating parties. So anyone can encrypt a message using another user's public key. The private keys are kept secret. So to encrypt a message, you use the recipient's public key. To decrypt a message, the recipient uses their own private key to decrypt the message that was encrypted with their public key. For digital signatures, to sign a message, you use your own private key. To validate a signature, you use the sender's public key. Each party has both a private key and a public key in asymmetric encryption. So if we're sending messages back and forth with asymmetric encryption, we each need a private key to decrypt the message sent by the opposing party encrypted with our own public key. The scenario we saw in that example a moment ago often comes in the form of certificates, which contains a public-private key pair, and the trust model explains how different certification authorities, which issue certificates, trust each other, and how their clients will trust certificates from other certification authorities. The 4 main types of trust models that are used in public key infrastructure, in certificate services that is, are bridge, hierarchical, hybrid, and mesh. We'll dive into PKI a bit further in just a couple of minutes in case you're unfamiliar, so let's put a pin in that. I want to talk about key management for a moment, and key escrow addresses a common problem. That is the possibility that a cryptographic key may be lost. The concerns usually come with symmetric keys, that single shared key scenario, where if we lose that key, our data is encrypted and can't be decrypted, or with the private key in asymmetric cryptography, the key that is not shared. Now, if that occurs, there's no way to get the key back, then the user can't decrypt the message in either case. So organizations establish key escrows to enable recovery of lost keys. So having a copy of those keys with a third party, with an external entity. Now let's talk key management strategy for our encryption key lifecycle. So encryption keys should be generated within a trusted, secure cryptographic module, and they should use strong random keys using cryptographically sound inputs like random numbers. FIPS 140-2 validated modules provide tamper resistance and key integrity. We'll dive into FIPS 140-2 and a couple of other spots in the series. Now, encryption keys should be distributed securely to prevent theft or compromise during transit. We talked about that challenge of key distribution with symmetric algorithms. Best practice is to encrypt keys with a separate encryption key while distributing to other parties. That's where we can take that symmetric key, that shared key, and encrypt it for transport using an asymmetric algorithm. And you want to plan for securely transferring symmetric keys and distributing keys to the key escrow agent as well. So in case a key is lost, we can recover and decrypt that data. In terms of storage, encryption keys must be protected at rest and should never be stored in plain text. And this includes keys in volatile and persistent memory. So we shouldn't have a scenario where our encryption keys remain unencrypted in memory of a computer or other device. That concept of secure storage extends to a key stored in a key vault or on a physical device, really anywhere that key may be stored. And we also want to consider handling in the process of storing copies for retrieval if a key is ever lost. That concept of key escrow we discussed a moment ago. Usage focuses on using keys securely, primarily for access controls and accountability, authentication and authorization. Revocation refers to a process for revoking access at separation, like employee separation, or in the event of a policy breach, or a device or key compromise. Perhaps a private key has been compromised and stolen through an infected workstation. Then we need to revoke that compromised key. Now, if that compromised key were the private key of a certificate in a PKI scenario, we would revoke the certificate on the issuing certification authority. We also need a process for archiving keys no longer needed for routine use in case they are needed for existing data. Now, key destruction is the removal of an encryption key from its operational location. That's the last phase of the key lifecycle. And key deletion goes further and removes any information that could be used to reconstruct that key. For example, mobile device management systems remove certificates from a device during a device wipe or retirement. I'm talking about MDM systems like Microsoft Intune or AirWatch. So for the exam, you will want to understand where encryption can be deployed to protect the organization's data and systems. And not only knowing the layers and the services where you can enable encryption, but also your options for key storage and management, and some basics about whether keys are CSP managed or they're self-managed and why that would make a difference. So for key storage, many of your CSPs offer FIPS-compliant virtualized HSMs. That's the hardware security module that we can leverage to securely generate, store, and protect our secrets, our cryptographic keys in this case. Now, self-managed keys are typically not the default, and they may have a cost. It's worth understanding what would drive the need to self-manage your keys, because the CSP is, generally speaking, always going to default to offering to manage those keys for you. So organizations that use multiple cloud providers may need to retain physical control over key management. and use a BYOK or bring your own key strategy. So do know that generally to let the CSP manage the keys is a good idea unless you have requirements that mandate your organization manages the keys. For example, regulatory compliance sometimes necessitates BYOK or self-managed strategies. To recap, multi-cloud and regulatory compliance are two scenarios that can drive the need for BYOK or self-managed key functionality. There are a few other cloud encryption scenarios related to storage, cloud services, and applications you should be familiar with on the exam. We'll touch on a few of those here, starting with storage level encryption. That's encryption of data as it's written to storage, utilizing keys that are controlled by the CSP, at least by default, unless you opt otherwise. And generally speaking, you'll find that your CSPs now, AWS and Azure, for example, will encrypt data in their storage accounts by default, just out of an abundance of caution. Volume level encryption provides encryption of data written to volumes connected to specific VM instances, utilizing keys controlled by the customer. The underlying technology in this case is quite usually BitLocker for Windows and dmcrypt for Linux. And then we have object-level encryption, which is encryption of objects as they are written to storage, in which case the CSP likely controls the keys and could potentially access the data. That would typically be an insider scenario, a malicious insider, but possible. So to give you a bit of context, I want to do a little show and tell of storage-level encryption in the cloud. And again, the CCSP exam is cloud service provider agnostic. I'm going to show you an example in Microsoft Azure. AWS has similar functionality. You're not going to see any hands-on questions on the exam, but this will be important context to help you understand what's typically available and how it works. So here on the Microsoft Azure portal, I'll click on Storage Accounts, and then I'm going to click on one of my existing storage accounts, and we'll start under Encryption. And here I can see with the message, by default, this storage account is encrypted. It encrypts the data as it's written into the data center and then automatically decrypted when we access it. And for storage services in your major cloud service providers, Azure, AWS, Google Cloud Platform, I would say that's generally speaking the default. You'll notice that infrastructure encryption is possible, so this is an additional layer of encryption, a second layer of encryption they sometimes call double encryption. And you'll also see here that it shows me that Microsoft is managing the keys, but we do see that there's a customer managed keys option, should that be necessary for my scenario. Now I'm going to scroll down a bit and look at some other security related settings. So I see here that we can require secure transfer. That means we are disallowing HTTP without that TLS encryption. We are disallowing unsecure versions of server message block commonly used in file services. I can allow or disallow blob public access, so I can configure even anonymous access if my scenario requires it. And I can also allow or disallow account key access. When we disable this, any requests to the account that are authorized with a shared key would be denied. Disabling that setting once enabled could allow me to reverse a previous decision that I regret. Now I'm going to go up under Data Management here and click on Data Protection and just see what other features are available to me here. So I see I can enable operational backup with Azure Backup, point-in-time restore, soft delete. Think of soft delete as a recycle bin for your deleted items from your storage blobs or containers. We can enable permanent delete for soft deleted items, some version tracking, and a blob change feed, so really some audit trail of a fashion. And if I scroll up here under networking, I'll click on networking under security and networking. You'll see here that I can enable or disable public network access. I can enable from selected virtual networks and IP addresses. And you see I can add existing virtual networks or new networks. And then I also have a resource firewall here, a storage resource firewall. I can add my own IP address. You see it automatically identifies my IP, but I can add IP addresses or CIDR ranges. And when I scroll down here under exceptions, you'll notice that they allow Azure services on the trusted services list to access this storage account. That's going to be very handy if we're using multiple Azure services and we need one of those services to access data in this storage account. And that concept of essentially a resource firewall that we see here is not specific just to storage. You'll see resource firewalls come up in multiple cloud service contexts, enabling us to restrict the flow to cloud services from the internet. So we see here in the storage example, that's definitely a handy feature. So I hope that little show and tell was helpful. So back to our cloud encryption scenarios. Next up is file level encryption, which is implemented in client apps, word processing apps like Microsoft Word, or collaboration apps like SharePoint. How encryption is implemented will vary by app and CSP platform, of course. Then there's application level encryption, which is implemented in an application typically using object storage. Data entered by the user is typically encrypted before storage. And then we have database level encryption. This is transparent data encryption. It encrypts database files, logs, and backups. We have column level and row level encryption, as well as data masking. Now the functionality is going to vary by your relational database management system. So Microsoft SQL functionality will differ slightly from MySQL and PostgreSQL. Typically they all have some flavor of every one of these options. You'll need to be familiar with data obfuscation techniques for the exam, and I thought we'd cover these through an example, a use case. Reducing our GDPR exposure. So if we wanted to reduce or eliminate our GDPR requirements, we could try data anonymization, which is the process of removing all relevant data, so it's impossible to identify the original subject or person. If we do this effectively, GDPR is no longer relevant for the anonymized data. On the other hand, we can no longer recognize the original subject or person, so this is only good if we don't need the data. Anonymization is sometimes called de-identification. In fact, de-identification was the term used in the 2019 version of the exam. We don't see that in the syllabus any longer. Then we have pseudonymization, which is the de-identification procedure using pseudonyms or aliases to represent the other data, the original subject or person. This can result in less stringent requirements than would otherwise apply under GDPR. You want to use this if you need the data and you want to reduce your exposure. I find it helps to explain hashing by talking about how hashing is different from encryption. So encryption is a two-way function. What is encrypted can be decrypted with the proper key. Hashing is a one-way function that scrambles plain text to produce a unique message digest, conversion of a string of characters into a shorter, fixed-length value. There's no way to reverse a hash if it's properly designed. A few common uses would include verification of digital signatures, generation of pseudo-random numbers, and integrity services. So we see hashes used with a file hash, for example. I can hash a file, send it to another person. They can then produce the hash for that same file. If I'm using the MD5 hash, for example, if the recipient produces the MD5 hash and it matches the hash of the original file, we know that the integrity is intact. We received the same file that was sent. But that file hash comparison is far and away the most common that comes to mind. So a good hash function has 5 requirements. They must allow input of any length. They must provide fixed length output. And they make it relatively easy to compute the hash function for any input. They provide one-way functionality. What is hashed cannot be reversed. And it must be collision-free. And that collision problem is one of the reasons we don't see the MD5 hashing function used anymore. It's because it has a collision problem in certain scenarios. We'll see MD5 hashing used in file hashing in comparison, but that's really about it these days. So data masking. So we only have partial data left once we've masked data in a field. For example, a credit card would be shown as a series of asterisks with only partial data. We'll see a similar technique used for Social Security numbers. Commonly implemented within the database tier, but it's also possible in code of front-end applications. And we have another good opportunity here for a quick show and tell for database level encryption in the cloud. We'll take a quick look at Azure SQL Database. Again, the exam is CSP agnostic, and the features we look at here will vary by relational database management system, but this will give you a good idea of some of the features available for a PaaS database solution in a major CSP. So here in the Microsoft Azure portal, I click on SQL Servers and I see the server instances for the Azure SQL Database service. So if I click on one of these servers, I can scroll down here and under Data Management, I can see some information about backups. So there's a built-in backup feature in this PaaS service, and you'll notice it mentions databases are backed up automatically, and the backups are listed below. Now if I jump over to retention policies, I can see a bit more information. I can configure my retention policies it mentions, and my point in time restores are available from 1 to 35 days based on my preference, and my long-term retention policies enable me to keep full backups for up to 10 years. Definitely very relevant when we're talking about data retention later in this video. Now I'm going to go down just a bit further, and under security I'll click on networking, and here I'll see some familiar features. You'll notice I can enable or disable public network access, so it's either disable or selected networks. And if I scroll down, I can configure virtual networks. I can gate which virtual networks in my subscription can get to this particular service instance. If I scroll down a bit further, you see firewall rules. So again, that resource firewall functionality, so I can add an IP address or even a CIDR range. And when I scroll a bit further, I see the exception checkbox to allow Azure services and resources to access this server. And I'm now going to click on SQL databases, and we'll look at some database level functions under one of my database instances here. And again, I'm focused on security, so I'm going to scroll down, and under security I'll look at auditing. I see I have an option here to enable audit trail, so default audit settings include a set of action groups, so it's going to audit queries and stored procedures executed against this database, as well as successful and failed logins. Going a bit further down the list, I see dynamic data masking. And what I notice here is that it's even recommending a field that it suggests I mask, the email address field. That's going to be personally identifiable information of a sort for a user. And you'll notice here it tells me what the mask function looks like by default. So I have some native capabilities that are more or less provided for me with no additional effort, very little configuration effort. And just a couple of clicks down here in the menu, I see transparent data encryption, which is on here. So that's going to encrypt my database file, my backup files, and my log files. And just an FYI for later in this video, you'll also notice here a data discovery and classification feature. So when we're talking about data classification, mapping, and labeling a bit later, we see there's some built-in functionality here for our structured data. Another data protection and obfuscation technique called out in the syllabus is tokenization, where meaningful data is replaced with a token that's generated randomly, and the original data is held in a vault. It's stateless, stronger than encryption, the keys are not local. And I want to compare that to a technology we called out earlier, which is pseudonymization. It's a de-identification procedure in which personally identifiable fields within a data record are replaced by one or more artificial identifiers or pseudonyms. So reversal requires access to another data source. So in this case, tokenization goes further than pseudonymization, replacing your pseudonym with an unrecognizable token. Data loss prevention. So DLP is a system designed to identify, inventory, and control the use of data that an organization deems sensitive. It spans several categories of controls, including detective, preventative, and corrective. Policies can typically be applied to email, SharePoint, cloud storage, removable devices, and even databases. And it's a way to protect sensitive information and prevent its inadvertent disclosure. It can identify, monitor, and automatically protect sensitive information in documents, and that automation is a very common and important characteristic. It monitors for and alerts on potential breaches and policy violations like oversharing, but the protections travel with the document, file, or other data, preventing local override of DLP protections. And preventing local override is a key point there. So let's shift gears and talk keys, secrets, and certificate management. So keys are most often used for encryption operations, and they can be used to uniquely identify a user or system. Keys should be stored in a tool that implements encryption and requires a strong passphrase or MFA to access. In the cloud, that is typically a key vault, which we talked about in Domain 1. Now, secrets are often a secondary authentication mechanism used to verify that a communication has not been hijacked or intercepted. Certificates are used to verify the identity of a communication party, and they're also used for asymmetric encryption by providing a trusted public key. Remember, the trusted public key is used by the sending party to encrypt the data, which is then decrypted by the recipient using their private key, which hasn't been shared. And we also talked about how certificates and asymmetric encryption are often used to encrypt a shared session key or other symmetric key for secure transmission. So it helps us overcome that weakness of symmetric encryption, which is key distribution, secure key distribution. Next up, we have key management services. So all your CSPs offer a cloud service for centralized, secure storage of application secrets called a vault. And in Azure, that's Key Vault. In AWS, it's called Key Management Services. In Google Cloud Platform, it's Cloud KMS Vault. And a secret in this context is anything that you want to control access to, like API keys, passwords, certificates, tokens, or cryptographic keys. And the service will typically offer programmatic access via API to support DevOps and continuous integration and continuous deployment or delivery, which is CI/CD. Access control is generally offered at the Vault instance level as well as to the secrets stored within. So I think of that instance level security as management plane security, and then to the secrets, that's data plane security. But your secrets and keys can generally be protected either by software or by a FIPS 140-2 Level 2 validated HSM. This is a good opportunity for another quick show and tell of a service you may not have seen in the real world, and that's Key Vault for secrets management. So we'll take a quick look at some of the features in Azure Key Vault. I'm here in the Azure portal. I'm going to search for Key Vault, and I'll look at one of my existing Key Vault instances here in Azure. I'll look under Access Control. This is where we configure access to the Key Vault itself, that management plane security. I'm going to click on Add, Role Assignment, and here I see a number of existing security roles with Key Vault in the name, which give me options for easily assigning least privilege access to delegates who need access to this Key Vault, so I can give them just enough permissions. Now under Access Policies, I can configure the permissions at the data plane to the secret types and the operations themselves. We're going to look at my permissions at the data plane here, and I see I have permissions for keys, for secrets, for certificates. And I'll scroll down here. I see some other privileged operations, some key rotation permissions. So quite a lot of granularity in permissions there. Now I'm going to jump down to the Objects menu here, and here I'll see my secret types. I have keys, secrets, certificates, and if we look at keys, I'll just click Generate or Import, and I can generate or import or restore a key from backup. We see I can choose my key type here, RSA or elliptic curve, my key size. I can set activation and expiration dates. I can enable or disable this key. I have rotation policy options, exportability. Now, more interesting perhaps are certificates, and I think you'll find, generally speaking, some advanced functionality across all your CSPs. We'll look at the Azure capabilities here. So I can generate a new cert, I can import an existing. I see here I can create a self-signed certificate, perfectly okay for development purposes, but I can also issue a certificate from an integrated CA or a non-integrated CA. So an integrated CA in this case is a trusted certificate authority that has been integrated into Azure Key Vault to provide enhanced lifecycle capabilities. So you'll notice here I can automatically renew the certificate at a given percentage lifetime or a number of days before expiry. So I have some advanced functionality here. And we'll go away from here. I want to look at the properties just to show you one more area where we see some advanced functionality built into the Key Vault feature. So there's a soft delete feature, think recycle bin for Key Vault. So the soft delete's been enabled for this vault. And we can also set a retention period for deleted vaults and secrets. So you see for deleted vaults we have 90 days and we have purge protection. So if we enable purge protection, it enforces a mandatory retention period for deleted vaults and vault objects. So I have quite a lot of functionality in the Key Vault. So that's just a quick tour. If you've never seen a Key Vault before, now you have. Next, I want to look at digital signatures with you. Digital signatures are similar in concept to handwritten signatures on printed documents that identify individuals, but they provide more security benefits. It's an encrypted hash of a message, encrypted with the sender's private key, and in a signed email scenario, it provides 3 key benefits. Authentication, it positively identifies the sender of the email. Ownership of a digital signature secret key is bound to a specific user, so it gives us non-repudiation. The sender cannot later deny sending the message. This is sometimes required with online transactions. And integrity, it provides assurances that the message has not been modified or corrupted. Recipients know that the message was not altered in transit. These basics should be more than enough for the CCSP exam if you see a digital signatures question. So key management refers to the management of cryptographic keys in a crypto system, and operational considerations include dealing with generating keys, exchanging these keys, storing these keys securely, their use, destruction of keys at the end of their life cycle, crypto shredding we talked about earlier, as well as replacement of keys when they are lost or compromised. Design considerations would include cryptographic protocol design, your key server configuration, the number of key servers, their roles, user procedures, and other relevant protocols. Now, the certificate authority, sometimes called a certification authority, depending on the vendor you're working with. Certificate authorities create digital certificates and own the policies related to those certificates. And a PKI hierarchy can include a single certificate authority that serves as the root certificate authority and the issuing authority, the one that's issuing the certificates. This is not recommended. The reason being, in a single layer PKI hierarchy, if the server is breached, no certificate, including the root certificate, can be trusted. Your entire PKI hierarchy at that point is suspect and untrustworthy. Let's talk certificate types for a moment. So we have a user certificate that's used to represent a user's digital identity, and more often than not, that certificate is mapped back to a user account. A root certificate is a trust anchor in a PKI environment. It represents the root certificate authority from which trust of the entire chain is derived. In a conversation where entities, be those users or servers, are authenticating one another with certificates, each side must trust the root of the opposing side. If it's not trusted, the certificate's not going to be accepted. But that root is the root certificate authority. A domain-validated certificate is an X.509 certificate that proves ownership of a domain name. And extended validation certificates provide a higher level of trust in identifying the entity that's using the certificate. These are commonly used in the financial services sector. And our PKI hierarchy includes an issuing CA, a subordinate CA, or intermediate or policy CA it's sometimes called, and the root CA, or certificate authority. So let's look at the roles of these three in a bit more detail. So the root certificate authority is usually maintained in an offline state. It issues certificates to new subordinate certificate authorities, and the root CA, other than when it needs to issue those certificates, where there's an operation where it is absolutely required, it's powered off. The subordinate CA is also called a policy CA or an intermediate CA. It depends on the vendor you're working with. But that subordinate CA issues certificates to new issuing CAs. And the issuing CA is where certificates for clients, servers, devices, websites, etc. are all issued. All of your day-to-day certificate issuance comes from here. So that path, that chain from the issuing CA up to the root, is your chain of trust. And we could consolidate these functions into fewer servers. You can have a 2-level hierarchy or even a single-level hierarchy, but you're going to have a less resilient public key infrastructure. In that single-level hierarchy, if the server is compromised, your root of trust is compromised as well. So your entire PKI is blown. At that point, you have to go to ground. In a 3-tier hierarchy, if the issuing CA is compromised, we can recover without having to reestablish the entire org. So let's just unpack a few important details about that subordinate CA, that intermediate CA, and talk about how it helps us in the event of compromise. So the subordinate CA regularly issues certificates, so typically we don't have them staying offline as often as you would a root. They do have the ability to revoke certificates, making it easy for us to recover if a breach does happen. So if we have a breach at an issuing CA, the subordinate can revoke that issuing CA certificate. We can issue a new one and deploy a new issuing CA. Now, any certificates coming from that issuing server that was compromised, those will have to be reissued as well, but we can recover. So when that issuing CA is breached, we just revoke the certificate and issue a new one and then reissue those affected client certificates. But a single compromised CA does not result in compromise of the root when we have that multi-tier hierarchy. If we have 2 or 3 layers, we're good. So let's talk about the certificate revocation list, which contains information about any certificates that have been revoked by a subordinate CA due to a compromise to the certificate or the PKI hierarchy. CAs are required to publish CRLs, but it's up to certificate consumers, the client, if they check these lists and how they respond if a certificate has been revoked. So it's up to client behavior. So let's talk about certificate revocation. So revoking or invalidating a certificate before it has actually expired. A certificate in this case is effectively canceled and the certificate serial number is added to that certificate revocation list, or CRL. But parties checking the certificate to verify identity or authenticity must check the issuing authority on validity. 2 potential options for tracking revocation are to ask for the CRL, or if available, the OCSP endpoint or service, the Online Certificate Status Protocol endpoint. The endpoint to query for CRL or OCSP is actually listed on the certificate itself. And if the other client or service, again, doesn't check the CRL or the OCSP for validity, they may accept an invalid certificate as valid. The benefit of Online Certificate Status Protocol is that it offers a faster way to check a certificate status compared to downloading a CRL, which contains a list of all the certificates that have been revoked in that organization, and that list can grow quite long. So it's not great performance. With OCSP, the consumer of a certificate can submit a request to the OCSP endpoint listed on the certificate to obtain the status of a specific certificate. Now, a certificate signing request records identifying information for a person or a device that owns a private key as well as information on the corresponding public key. It's the message that's sent to the CA in order to get a digital certificate created. And the common name is the fully qualified domain name of the entity, like a web server, which you'll see on a certificate. You'll see a CN. It might help you if we take just a minute and look at these properties on an actual certificate. So if you just click the Windows key on a Windows machine and type certificates, you'll get the certificates snap-in. And I'll go to Trusted Publishers and Certificates, and I'm going to look at this VPN certificate I use for testing every now and again. And I click on that cert and it brings up the properties here. If I go to Details, I can see the serial number of the cert, the signature algorithm, so the cryptographic algorithm used, validity, to and from dates. If I scroll down just a bit, here under the subject, I'll see that common name, the CN I mentioned, right there on the top line. And I scroll a bit further, I can see the usage of this certificate, so it's a code signing cert. I see the CRL distribution point. So the CRL distribution point, or CDP, gives us the path to the certificate revocation list, and you see it's expressed in the form of a URL, which ends in a file with a .crl extension. Scroll down a bit further, if I look at Authority Information Access, this is where the OCSP endpoint is published, the Online Certificate Status Protocol endpoint, and there you'll see that's also expressed as a URL. So it's really just up to your client to make the call. And moving on, that brings us to 2.4, which is Implement Data Discovery. And in this section, we'll be focused on structured data, unstructured data, and new in the 2022 exam, they mention semi-structured data directly here in the syllabus. And we'll also talk about the effects of data location on the data discovery process. Let's start with a look at structured data. This is data that's contained in rows and columns like an Excel spreadsheet or a relational database. So Microsoft Excel, Microsoft SQL, MySQL, PostgreSQL, MariaDB, all relational databases that would fall into this structured category. It often includes a description of its format known as a data model or a schema, which is an abstract view of the data's format in a system. We'll often hear relational databases referred to as schematized data. And the data is structured as elements, rows, or tuples, and given context through that schema. So how do we discover data, sensitive data, in a structured database? Well, metadata that describes the data is a critical part of discovery because it will give us some hint as to what the data represents. Semantics, or the meaning of the data, is described in the schema or the data model and explains relationships expressed in data. Next, we have unstructured data. This is data that cannot be contained in a row-column database, and it does not have an associated data model. There is no schema. Images, video files, social media posts generally fall into this category. Discovery occurs through content analysis, which attempts to parse all data in a storage location and identify sensitive information. So how does that content analysis, that discovery, take place? Well, there are a few methods. Pattern matching is one, which compares data to known formats like credit card numbers. DLP tools often have predefined sensitive data types that will look for credit cards, social security numbers, banking information, and the like. And many of these DLP tools will have some image-based recognition as well, some OCR and other capabilities. There's lexical analysis, which attempts to find data meaning and context to discover sensitive information that may not conform to a specific pattern. And then there's hashing, which attempts to identify known data by calculating a hash of files and comparing it to a known set of sensitive file hashes. This is only useful for data that does not change frequently. And then there's semi-structured data, which is a combination of structured and unstructured data. Quite often it's unstructured content that contains metadata that facilitates organizing the data. It's fluid, but it's organizable by properties or metadata. Good examples here would include JSON, XML, HTML, email messages, NoSQL databases. This is really a mix of data types that will require a combination of discovery methods and tooling capable of discovery in these commingled data types. So really it's going to take elements of structured and unstructured discovery to fully discover data in a semi-structured scenario effectively. But let's talk about that a bit further in the context of data location and discoverability. The location of data will impact both its discoverability and the choice of tools we use to perform discovery. So tools must be able to access data to perform the scanning and analysis needed in the discovery process, of course. This may require different tools for cloud and on-premises discovery. Not all cloud solutions may offer a local agent for on-premises, something we need to consider in tool selection. Network-based DLP tools may not analyze all traffic between on-premises endpoints and the cloud, so another consideration. An optimal DLP approach will discover data in on-premises and in cloud repositories as well as data in transit. Well, why would that be important? Well, where the data is going could matter, right? If we have a sensitive email going out and that's going from one employee to another who are both authorized to see the data, that may be no problem. But if that email is going to an external party, we may want to encrypt that automatically on the way out the door so the recipient can't read it. The same could be true of oversharing of sensitive data through a collaboration platform like SharePoint. If we can't evaluate our data in transit, there's potentially a big gap there that leads to data leakage. And our tools must be able to scan unstructured data within structured data sources like relational databases. A good example of this would be a problem description inside a help desk ticket stored in a SQL database. We have a problem description that's just unstructured free text, but it's stored within a structured data repository. So when we have both structured and unstructured data in the same repository, it's often going to increase our tool cost and complexity. It may also present classification challenges. We might not be able to classify that specific row of data if our tool won't support it. And that can lead to some less attractive consequences. If we have to put a single classification label on a large data source, the most sensitive classification found would apply. So in the case of that help desk ticket stored inside a SQL database, if there's sensitive data within that ticket, we might have to put a single very sensitive classification on a large repository that has a bunch of less sensitive data there. So tooling will matter in that case. So data discovery ensures that data is appropriately classified for protection. Discovery is really the first step, so we can then classify. So metadata-based discovery is a list of traits and characteristics about specific data elements or sets. It's often automatically created at the same time as the data. And then there's label-based discovery, which is based on examining labels created by the data owners during the create phase of our secure data lifecycle. Or we can do that in bulk with a scanning tool often, which may use built-in sensitive data types that I described earlier. You might see this used with structured data with a relational database. It's certainly going to be much more common with file data. That brings us to 2.5, which is implement data classification. Once we've discovered our data, we're now going to classify. We'll talk about data classification policies, data mapping, and data labeling. So let's just do a simple comparison of data classification in the government context versus a public entity or a commercial company. So at the lowest level of classification, we have unclassified data, what we'd call public data in the non-government space, so no damage if exposed. One level higher, we have confidential or sensitive data where the organization is going to sustain some damage. Now, the type of damage that the organization would sustain in the government context at a certain level of classification, we're talking about national secrets that could endanger human life. In the public context, we're talking about corporate reputation, competitive disadvantage, or monetary loss. The next level of classification, we have secret, or what we call private data on the public side, where the organization could sustain serious damage. And then at the highest level of classification, we have top secret and confidential or proprietary. And we see some common terms here, right? We see serious damage at the secret level/private level, and then for top secret or confidential, we see exceptionally grave. And non-government scenarios are often called commercial or public. So let's talk through some common sensitive data types you'll want to know for the exam. The first is personally identifiable information, or PII. That's any information that can identify an individual, their name, social security number, birth date or birthplace, biometric records. We have protected health information, or PHI, which is health-related information that can be related to a specific person. PHI is actually regulated by HIPAA High Trust. And then cardholder data. That's allowable storage of information related to credit card and debit cards and transactions. That's defined and regulated by PCI DSS, which isn't regulated in law. That was a standard put together by the big four credit card companies. Now let's talk data policies. We have a data classification policy, which would be labeling or tagging of data based on type, like PII or PHI that we just described. You could have data retention policies that ensure legal and compliance issues are addressed, retaining data for a period of time as specified in law. And then we have regulatory compliance, which for legal and compliance reasons may require us to keep certain data for different periods of time and will drive classification. It's going to be a driver of classification and retention. Just a couple of simple examples. Some financial data needs to be retained for 7 years by law, and some medical data may need to be retained for 20 to 30 years, and we'll need to classify that data appropriately. Going a bit further, data classification is a process for categorization of data and defining the appropriate controls based on that category. So categories could include the data type based on its format or its structure, jurisdiction or any other legal constraints, ownership, the context of the data can be important, contractual or business constraints, think PCI DSS, which is contractually enforced, trust levels and the source of origin, value, sensitivity, criticality. We want to protect intellectual property, trade secrets, and retention and preservation. Again, retention and preservation may be driven by regulatory compliance requirements or even legal proceedings. But data should be classified as soon as possible after creation. We'll go back and look at that secure data lifecycle here in a couple of minutes, and I'll remind you of where that happens. But we classify as soon as we can after creation so we can get protection in place. So mapping and labeling. So mapping informs the organization of the locations where data is present within applications and storage. It brings understanding that enables implementation of security controls and classification policies. Usually precedes classification and labeling, though. Labeling goes hand in hand with the mapping process, and labeling requirements that apply consistent markings to sensitive data should accompany classification. It's often applied through classification policies in DLP tools, providing a target for data protection. It's often applied in bulk using classification tools, but we discover our data, we map our data, we label our data, we classify our data, and then we protect our data. And I've talked a fair bit about the DLP process here and DLP tools, and it does occur to me that maybe you've never seen one. Maybe that's not been your role. So I think this is a great opportunity for some quick show and tell. I'm going to show you data discovery, mapping, labeling, and classification in Microsoft's cloud-based DLP solution. For a quick example of data loss prevention and information protection functionality, here is the Microsoft Purview portal at compliance.microsoft.com, and I'll start under data classification. I mentioned that some of your DLP solutions have some predefined sensitive information types. So Microsoft, for example, has over 300 here, and if I type words like driver, for example, I see predefined information types that will help me to identify driver's license numbers. There should be a credit card number identification, a sensitive info type. If I type social, I'll see social security numbers for a variety of countries. So many predefined information types. Now you can create your own custom types using regular expressions and other matching capabilities, but a lot out of the box. And there's the concept of trainable classifiers, so I can train the system to recognize documents for what they are, bank statements, my company's invoices, and the like. And you'll see that there are several here that are published off the shelf, and we can train these to be smarter based on our company's documents. So just worth noting we have that off the shelf. And I'll go over to the Content Explorer tab here under Data Classification, and the system will show me sensitive information types for which the system has already identified documents and data. For example, for all full names, it shows me 350 matches, and it shows me the repositories where it's found that information. So whether it's Teams, SharePoint, OneDrive, Exchange, so whether it's email, collaboration, or chat, US driver's license number, similar capabilities, and I can drill down to see what it's found just to make sure that it's matching as I expect. And then real quickly, I want to show you the label policy and auto labeling capability. So I'll go down the menu here to information protection, and here I'll find the labels, and I see some default labels have been created for general, public, confidential, highly confidential. Here's a confidential finance. And when I go to label policies, this is how I publish a label to my users so they can apply these labels from their Office apps or in SharePoint sites or in email. And once published, they can apply those labels to protect their document. Now I'll go over to the auto labeling policy tab here, and I'll click on Create Auto Labeling Policy just to show that we can pick the info easily that we want this label to be applied to. So for example, my company's in the United States, I'll pick United States of America, and now I can see some of the categories and the templates that are created for me in advance. So GLBA, HIPAA, US Patriot Act. When I go to financial, I see PCI DSS, medical and health, there's HIPAA. So we can create these auto labeling policies using off-the-shelf functionality that's been created for us. And then I can choose the locations where I'd like to apply that label, or I can even configure some custom functionality there. And every platform is going to be different, but in the enterprise space, what you're going to find is that many of your DLP and information protection solutions have this sort of enhanced functionality right off the shelf. Okay, I hope that little show and tell was helpful. Now I'd like to revisit with you the secure data lifecycle, looking at the lifecycle through the lens of data classification. So as we've said in the past, data can be created by users, data can be created by systems, but after that data is created, we need to classify that data as soon as possible. It's only through classification that we can then determine appropriate protections for that data. Ideally, the data will be encrypted at rest regardless of its sensitivity. And data should be protected by adequate security controls based on its classification. So classification will drive the need for protection. And as data is used and modified, classifications may change. So our process of scanning and labeling and classifying data is an iterative process. We're scanning these repositories repeatedly. Certainly a user may reclassify a document when they take a harmless, low sensitivity Word document and incorporate protected health information into that document, but we also need an automated bulk classification process that's going to catch those changes and reclassify that data on the fly. And then as data is shared, of course, when we're transmitting data over a network, sharing a document through a collaboration platform like SharePoint, we need to make sure that we protect that data from data leakage. If we have sensitive company information in a document, it may be fine for that data to be shared in that document within our employees, but we want to block that sharing to external entities, whether that's going through just a simple share link or through the email channel. We need to have data loss prevention capabilities to help us to secure our data and prevent that leakage in use. So data protection policies may block external sharing many times. And archival, again, is sometimes driven by laws or regulations that require us to retain data for a specific period of time, and classification can drive data retention policies. For example, the organization's annual financial reports would be classified as financial data, and that sensitive data classification will drive retention of that data based on the type of information in that document. And when data is no longer needed, it should be destroyed in a way that it is not readable nor is it recoverable. But classification really drives the rest of the life cycle if you look at it from this perspective, including destruction. And that brings us to section 2.6, Design and Implement Information Rights Management. Only 2 topics in this section, IRM objectives and appropriate tools. So let's start with a definition of information rights management. So an IRM program is designed to enforce data rights, provisioning access, and implementing access control models. It's often implemented to control access to data that is designed to be shared, but not freely distributed. It can be used to block specific actions, like print, copy-paste, download, and sharing. And it can provide file expiration so that documents can no longer be viewed after a specified time. Many popular SaaS file sharing platforms implement these concepts as sharing options, which allow the document owner to specify which users can view, edit, download, and share, and for how long. This always includes a cloud service. It may also include a local agent. The objectives of information rights management. One is persistence. Our ability to control access, to enforce our restrictions, must follow the data, meaning protection must follow that document or data wherever it travels. Dynamic policy control. So an IRM solution must provide a way to update the restrictions even after the document has been shared. IRM tools can enforce time-limited access to data as a form of access control. The ability to expire or revoke access require the user to check in from time to time to see if they still have access, to contact that cloud service as a prerequisite for continuing access. Continuous audit trail. An IRM solution must ensure that protected documents generate an audit trail when users interact with protected documents. It's required for accountability and non-repudiation. Interoperability. IRM solutions must offer support for users across different system types. We need support for Windows and Mac OS, desktops, laptops, mobile phones, tablets, and different apps will be important. Appropriate tools. So IRM tools comprise a variety of components necessary to provide policy enforcement and other supporting attributes of that enforcement capability. So a centralized service is one for identity proofing, certificate issuance, store of revoked certificates and access, and for unauthorized identity information access. This enables enforcement from anywhere. Secrets storage. So IRM solutions require local storage for encryption keys, tokens, or digital certificates used to validate users and access authorizations. Local storage requires protection primarily for data integrity to prevent tampering with the material local to the device used to enforce information rights management. But IRM must prevent local modification of access controls and credentials. Otherwise, a user might modify the permissions granted to extend their access beyond what the data owner originally specified, whether that's extending the period of time or the level of access. Bottom line, local changes must never supersede controls implemented by the cloud service. Now, since certificate revocation was called out in the syllabus in section 2.6, I want to revisit the key management strategy for the encryption key lifecycle just to touch on certificate revocation, which we talked about a bit earlier. So the process for revoking access at separation, policy breach, device or key compromise happens in the revocation stage. And how exactly that revocation goes down will depend on the IRM solution you're working with, but if we think about it in the PKI context with certificate revocation, you would revoke the certificate on the issuing certificate authority Presumably you would remove access, control settings for a particular user, revoke that access, and the IRM solution would handle some of this in the background for you. But at the end of the day, that revocation of the certificate would be recorded on the certificate revocation list and activity logged as part of the audit trail. So let's talk about intellectual property protections for just a moment. And I want to talk about intellectual property not because you will be tested on this directly, but because I see these mentioned in part at least in the official study guide and to a lesser degree in the common body of knowledge. So I think the basics of intellectual property protections in the U.S. may be something you're just expected to already have knowledge of. So we'll touch on these just briefly. So there's trademarks, which cover words, slogans, and logos used to identify a company and its products or services. So that would be a trademark to cover the Apple logo, for example, or Nike's slogan, "Just Do It." A trademark lasts 10 years, it can be renewed. Patents protect the intellectual property rights of inventors. A patent provides the inventor exclusive use of their invention for a period of time, generally 20 years. And filing requires public disclosure, which is undesirable in some cases. That's where trade secrets come into play. Intellectual property of an inventor that is absolutely critical of their business and must not be disclosed is a great candidate for a trade secret. It's valid as long as secrecy is maintained and not discovered by others. Once it's no longer a secret, protection is lost. And then there's copyright, which is automatically granted to the creator of a work upon creation, but can be registered. It prevents others from reusing. And copyright protection lasts 70 years beyond the creator's death. Then the work moves into the public domain, where it is freely reusable. And that brings us to 2.7, plan and implement data retention, deletion, and archiving policies. So here we'll touch on data retention policies, data deletion procedures and mechanisms, data archiving procedures and mechanisms, and the concept of legal hold. So I want to revisit the secure data lifecycle with you in the context of retention and data destruction. So retention is driven by security policies and regulatory requirements. Retention happens here between archival and destruction. Audits or a lawsuit may require production of some data, and that may trigger retention. Now, Sarbanes-Oxley, for example, requires tax returns are kept for 7 years, and payroll and bank statements are kept forever. Sarbanes-Oxley is a regulatory requirement of every publicly traded company in the U.S. Now, when data is no longer needed, it should be destroyed in a way that it is not readable. And keeping data longer than needed increases risk, and organizations know this. They know they cannot produce data that they do not have for a legal case. So when data hits the end of its retention requirement, it should be destroyed. And that's where crypto shredding, secure destruction, comes into play. We touched on crypto shredding briefly in Domain 1. We'll touch on it again here. So this is cryptographic erasure. Data is encrypted with a strong encryption engine. The keys used to encrypt the data are then encrypted using a different encryption engine. Then keys from the second round of encryption are destroyed. On the pro side, data cannot be recovered from any remnants. The downside here is high CPU and performance overhead. There's a lot of processing involved. Now, if the exam poses questions on secure data destruction, this is almost certainly the answer. But know the steps of crypto shredding for the exam. So data archiving refers to placing data in long-term storage for a variety of purposes. The optimal approach in the cloud differs in several respects from the on-premises equivalent. So key elements of data archiving in the cloud: data encryption, data monitoring, e-discovery, and retrieval. We need all of these capabilities. Backup and DR options. And the data format and media type do matter. We need to think about our ability to search and retrieve data from an archive. So let's talk about each of these 6 at greater depth. So we'll start with encryption. Our encryption policy should consider which media is used and our data search and restoration needs, as well as our regulatory obligations. We need the right balance of security and retrievability, searchability. What threats should be mitigated by the encryption? How will the encryption keys be managed? Long-term archiving with encryption can present key management challenges. Access controls and encryption are important to protect data integrity by preventing unauthorized access. Then we have data monitoring. So data stored in the cloud tends to be replicated as part of storage resiliency or business continuity and disaster recovery. To maintain data governance, it is required that all data access and movements be tracked and logged. Monitoring to ensure all security controls are being applied properly throughout the data lifecycle, also important. Accountability, traceability, and auditability should be maintained at all times. E-discovery and retrieval. Archive data may be subject to retrieval according to certain parameters like dates, subjects, and authors. This could be due to audit requirements or even a legal proceeding, but retrieval can definitely become important. The archiving platform should provide the ability to perform e-discovery on the data to determine which data should be retrieved. So we only retrieve the data that is necessary, the minimum necessary. Data that is subject to more frequent search should be kept in a service that enables e-discovery with a manageable level of effort. We need to ensure that staff can manage the e-discovery support burden. If we take logs and store them in a raw format in blob storage in the cloud, that's not going to give us great searchability. That's going to be high effort for our staff. So we need to balance the need for security and cost controls with our operational overhead. Then we have backup and DR operations. So all requirements for data backup and restore should be specified and clearly documented. And business continuity and disaster recovery plans are updated and aligned with whatever procedures are implemented. We need to know our options here. And when it comes to backup and DR of our archive data, both resiliency to disaster, ensuring archive data availability, and knowledge and control of data replication are both important. So data format and media type. This is an important consideration because it may be kept for an extended period, and the format needs to be secure, accessible, and affordable. Media type should support the other data archiving requirements, but physical media concerns fall to the CSP. At the end of the day, we want to make sure we are storing our data in a secure, easily accessible, but also affordable fashion. You're often paying by the gig in the cloud, so we want to be careful. Now, AWS S3 and Azure Storage both offer cool tier, infrequent access storage for low-cost archiving, and they, generally speaking, have an immutability flag you can flip to ensure integrity. You might get your data storage down to less than a penny a gig in those cool tier options, but your searchability, your accessibility is certainly going to be less versus keeping that accessible and indexed through an e-discovery feature. Often cloud storage is billed by the gig, so beware of cost. However, just balance with your access needs. That's the bottom line. That's your takeaway for the exam. And legal hold is called out explicitly in the exam syllabus, so let's touch on some details here. Legal hold protects any documents that can be used in evidence in legal proceedings from being altered or destroyed. Data protection suites in the cloud often have a feature to ensure immutability, which ensures that the data marked immutable cannot be modified. In fact, when we look at cloud storage like Azure Storage or AWS S3, they offer an immutable storage feature, so I can mark a container as immutable. When we think about data protection software, legal hold generally implements permanent retention until a human authorizes release when the possibility of production in legal proceedings has passed. A legal hold is sometimes called a litigation hold. And that brings us to another good opportunity for a quick show and tell. And we'll revisit that same cloud suite we explored for data classification, for labeling, and mapping, and we'll have a look this time at data retention. Again, just for some real-world context as you consume these concepts for exam day. So we're back again to the Microsoft Purview Compliance portal at compliance.microsoft.com, and to see the retention label functionality, I'll scroll down here to Data Lifecycle Management, and under Microsoft 365 I see retention policies, and here I will find some retention policies that have already been created. So for example, let's just click on Personal Financial PII, and I'll click on Edit so we can look at how this policy is configured. And I see here it has a name, a description, and they have options here for adaptive or static scopes. So I can configure a policy to be adaptive, where it automatically adapts based on labels and other functionality to include new locations in the retention policy. So we'll look at the current settings, which are static, and under here I can see that it's applied to multiple locations to different types of data. So we see email, we see collaboration with SharePoint, OneDrive, which would be our file data, more mailbox data, Skype for Business. So applying across a number of locations, but if I also look over here to the included column, I can see to whom and what this applies. So for example, I see it applies to all mailboxes, all SharePoint sites, all user accounts, all Microsoft 365 groups for the group mailboxes and sites. And let's have a look at our retention settings. So I see here it's applying for 7 years, and it's applying that retention when the items are created. You see I have the option here to change that to apply that 7-year retention to when the items were last modified. And then you'll notice I have some options here in terms of what to do at the end of the retention period. I can delete the item automatically, I can do nothing, I can retain the item forever, or only delete when they reach a certain age. So I have a number of functional options here in terms of what we call record disposition, what we do at the end of the retention lifecycle. And that's really all I have to show you on this one. Quite simple, really. And again, this is a CSP agnostic exam. This is purely just to give you a real-world example, to give you a bit of additional context for the concepts we were talking about here. And with our show and tell out of the way, we're now ready to move on to Section 2.8, Design and Implement Auditability, Traceability, and Accountability of Data Events. Our last section of Domain 2. We'll touch on definition of event sources and requirement of event attributes, logging, storage, and analysis of data events, as well as chain of custody and non-repudiation. So let's start with accountability. So accountability is maintained for individual subjects using auditing. Logs record user activity, and users can be held accountable for their logged actions. It directly promotes good user behavior and compliance with the organization's security policy. When folks know someone is watching, they tend to behave. Simple as that. Security audits and reviews. So these help ensure that management programs are effective and being followed. They're commonly associated with account management practices to prevent violations with least privilege or need-to-know principles. They can also be performed to oversee many programs and processes. So security audits and reviews are useful in maintaining programs like patch management, vulnerability management, change management, configuration management. Periodic audits and reviews to ensure our processes are being followed are helpful in a wide variety of areas. So let's talk about event sources and attributes in the context of auditability, traceability, and accountability of our data events. So OWASP provides a comprehensive set of definitions and guidelines for identifying, labeling, and collecting data events. It ensures events are useful and pertinent to applications and security, whether in a cloud or a traditional data center. So the definition of event sources, which events are important and available for capture, will vary based on cloud service model that we're employing, whether that's IaaS, PaaS, or SaaS. So let's take a look at that. And we'll start with IaaS, so with our IaaS event sources. Within an IaaS environment, the cloud customer has the most access and visibility into system and infrastructure logs of any cloud service model. That's because the cloud customer has nearly full control over their compute environment, including system and network capabilities. Virtually all logs and data events should be exposed and available for capture. This is because the customer has more responsibility than in any other cloud model. If you go back and look at the shared responsibility model in Domain 1, that becomes crystal clear. Moving on to PaaS event sources. A PaaS environment does not offer or expose the same level of customer access to infrastructure and system logs as IaaS. However, the same level of logs and events is available at the application level, again due to responsibility. Responsibility for system and infrastructure in PaaS belongs to the cloud service provider, so we have less access to those logs. And that brings us to software as a service. Now, because in a SaaS environment, the CSP is responsible for the entire infrastructure and application, the amount of log data available to the cloud customer is understandably less. Customer responsibility is limited to access control, shared responsibility for data recovery, and feature configuration. So in this case, service responsibility equates to log visibility. So let's take a look at the who, what, where, and when of logging from OWASP, where we find some excellent guidance. Ultimately, logs should be able to answer the question, who did what and when. Sufficient user ID attribution should be accessible, or it may be impossible to determine who performed a specific action at a specific time. This is called identity attribution. In my mind, this goes a step further. Now, this is what's necessary for non-repudiation. When I think of it, I think of who did what, when, and from where. I like to know a bit about the device and the location as well, but at the end of the day, who did what and when is the minimum we should be focused on. So in terms of who, OWASP advises we need source address and user identity if known. And the what would include type of event, severity of event, security relevant event flags if the log contains non-security events, as well as a description. And the where, application provider, application address, the service, geolocation, window 4-page, the URL, HTTP method, code location, the script of the module name, and the when. And for when, we see log date and time, event date and time, and the interaction identifier. So while the question we need to answer is who did what and when, you can see from the who, what, where, and when why I would also ask who did what, when, and from where. And you can find this OWASP guidance in the OWASP logging cheat sheets that they maintain for developers on building application logging mechanisms, especially related to security logging. You'll find these cheat sheets on GitHub at the URL you see here. I've also included that URL in the video description. You simply go to that URL, browse to the cheat sheets folder, and click on the logging cheatsheet.md. That's a markdown file. So logs are worthless if you do nothing with the log data. They're made valuable only through the process of review. That is, they are valuable only if the organization makes use of them to identify activity that is unauthorized or compromising. Now, a security information event monitoring tool can help solve some of these problems by offering some key features: log centralization and aggregation, data integrity, and normalization, giving us a standardized event format even when it's pulling data from many disparate sources. Automated or continuous monitoring, alerting, and investigative monitoring. Now, we will cover the SIM in depth in Domain 5, but while we're here, let's touch on these 6 key concepts that are called out. So the SIM features necessary to optimize event detection and visibility and to scale our security operations. So log centralization and aggregation, so rather than leaving log data scattered around the environment on various hosts, The SIM platform can gather logs from a variety of sources, including operating systems, applications, network appliances, user devices, providing a single location to support investigations. And when we have all those disparate sources of data, it gives us greater context as to how activities, including bad actors, are moving about our environment. It gives us a better idea of the scope of an incident. There's data integrity, so the SIM should be on a separate host with its own access control, preventing any single user from tampering. Very easy to do in the cloud. Normalization. SIMs can normalize incoming data to ensure that data from a variety of sources is presented in a consistent format. Automated or continuous monitoring, so sometimes referred to as correlation, SIMs use algorithms to evaluate data and identify potential attacks or compromises. And alerting. SIMs can automatically generate alerts like emails or tickets when action is required based on analysis of incoming log data. Investigative monitoring. So when manual investigation is required, the SIM should provide support capabilities such as querying log files and generating reports. So broad SIM visibility across the environment means better context in log searches and security investigations. When we can see into data, apps, identities, endpoints, and infrastructure all in one place, we're going to have a better idea of the big picture as it relates to a potential security incident or malicious activity. And you should be familiar with chain of custody, which tracks the movement of evidence through its collection, safeguarding, and analysis lifecycle. This is evidence in a legal proceeding. So what are the functions and importance of chain of custody? Well, it provides evidence integrity, if I were to coin a phrase. Through convincing proof, evidence was not tampered with in a way that damages its reliability. So it documents key elements of evidence movement and handling, including each person who handled the evidence, the date and time of movement or transfer, and the purpose for the evidence movement or transfer. So what if evidence is left unattended or handled by unauthorized parties? Well then, criminal defendants can claim the data was altered in a way that incriminates them, and thus the evidence is no longer reliable. Chain of custody is a foundational principle of evidence handling in legal proceedings. And you should also be familiar with non-repudiation. Non-repudiation is the guarantee that no one can deny a transaction. There are a few methods to provide non-repudiation. So systems enforce non-repudiation through the inclusion of sufficient evidence in log files, including unique user identification and timestamps. Digital signatures prove that a digital message or document was not modified, intentionally or unintentionally, from the time it was signed. Based on asymmetric cryptography, a public-private key pair. It's the digital equivalent of a handwritten signature or a stamped seal. We talked about digital signatures a bit earlier. I want to just reinforce this in your memory. It's definitely part of what you'll want to be familiar with on exam day. Multiple accounts make non-repudiation more difficult. If we have a user logging in with different identities, it's more difficult to track their movements and activities throughout our environment. Shared accounts make non-repudiation virtually impossible because we can then no longer tie individual actions to a specific individual beyond their ability to deny they performed those actions. And there we have it. Congratulations, you have made it to the end of Domain 2 in the CCSP Exam Cram series. I hope you're getting value from the series. If you have questions at any point as you're studying throughout the 6 domains, leave me a question in the video description. Reach out in LinkedIn chat, and I'll look forward to seeing you in the next domain. So until next time, take care and stay safe.